You're welcome. This is the House of Shedo. Don't forget to subscribe so you can get to access quality videos from the House of Shedo. Please subscribe. So we continue with our limit. Let's look at this question. Now, if you make a direct substitution, x tends to minus 3. If you make a direct substitution here, you have something of this nature. You have minus 3 square 9 minus 3 square plus 3 minus 3. So that is going to be, this is 9 minus 9 is 0, and this is 9 minus 9 is 0. Now this doesn't make sense. There is no mathematical number that is 0 over what? 0 is undefined. It's not a number. So one of the ways we are going to approach this is we are going to see how to try to simplify the expression before we make our direct what? Substitution, or we use the L'Hospital's rule to differentiate the numerator and the denominator before we make our direct substitution. So let me simplify. We'll have lim as, so when you simplify this, you can write the up as this, and then you can factorize what is down as this. Okay, and then definitely you can use difference of 2 square at the numerator to have something like this, and this can now cancel this. So with this now, I think you can make your substitution. This becomes minus 3 minus 3, and then minus 3, this minus 6 or minus 3, and I think this should be what? 2. So that means our function is actually approaching what? The number 2. You're welcome. This is House of Shedo. Now this is Math 121, and we want to see how to consider questions on limits. Limit itself is a very important concept in mathematics. In fact, it is one of the building blocks of mathematical analysis, but we are not here to talk about the theories of limits. We are here to see how to evaluate Math 121 kind of problems under limits. So having this particular question, we have, the question is like, let's find the limit of this function as the x approaches infinity. So we want to know what the function is going to approach, what value the function is going to approach as its argument approaches what? Infinity. And when you look at this, you see that it doesn't make sense to do a direct substitution. If you do a direct substitution, then you have a case of infinity over infinity, which does not go. So I think it would be wise to see how to simplify this expression by dividing all the terms of the expression by the leading power of the variable. So we say the expression can be written as x over x4, and then we have our 2 over x4, and then we have over x4 over x4. So we have done the same thing to each and every term of the expression, which is justified according to the rules of algebra. So we're going to have lim s tends to infinity. This is equal to 1 over x. This is 2 over x4. This is 5. And this is minus 3 over x. And this is plus 2 over x3. Now, it is much easier to find the limit now as s tends to what? Infinity, because this is a classic case situation whereby you have a constant as the numerator and you have the variable as the denominator. So as the value of x in the denominator increases, then the whole fraction is going to tend to what? To 0. So 1 over x definitely is going to tend to 0 as x approaches what? Infinity. S keep getting larger. Likewise 2 over x4, because you can see 2 is a constant. So this is also going to tend to 0. And then we have our 5. And then this will tend to 0 as well. This will tend to 0 as well. So at the end of the day, we have 0 over 5, which is 0. So the limit of this function is 0 as x tends to infinity. So we'll continue on our limit. We have the limit of sine 3x over 2x as x tends to 0. Now, making a direct substitution to this is going to be sine. Wow, this is not going to work. This 3 times 0 is 0, and sine 0 is definitely 0. And this is 0 over 0. This is not going to work. Let's see how we can simplify. Okay, to simplify this, we will need to expand this using our compound angle, but I think the easier way to go about this, to route this, is to use the L'Hopital's rule. So what we are going to do is to differentiate the numerator and the denominator at the same time. So differentiate sine 3x and we differentiate 2x. Okay, so the differentiation of sine 3x is definitely going to be 3 cos 3x. Don't forget the differentiation of sine theta is cos theta, but because we have a constant 3 here, we'll bring it to the front of the cos. Now you can do this actually using the differentiation rule that is called the function of a function. Okay, but we don't need to do it here because of time. So this becomes d over dx of 2x. The differentiation of this becomes 2. So we can now make our substitution. We have our limits. So make our direct substitution. This becomes cos 0 over 2. So cos 0 is actually 1. So we have 3 over what? 2 as our final answer. So we'll look at this particular limit question. We have as x tends to 0 of s squared over 1 minus cos x. Now if we make a direct substitution, we discover that this is going to be 0 and cos x, cos 0 is 1. So 1 minus 1 is 0. So 0 over 0, as we said earlier on, that it is not a number, it's undefined. So we are going to see how to either simplify the expression, but it's not looking like something that simplification is going to be helpful. So we are going to see how to use the L'Hopital's rule. So let's differentiate the numerator and the denominator. So the differentiation of x squared is 2x. And the differentiation of, okay, this is 2 terms as expression, so differentiate it term by term. The differentiation of 1 is 0, it's a constant, and the differentiation of cos x is minus sine x. Then the minus multiply this minus, that is going to give us sine x. And now we try again to make a direct substitution. if you substitute x is 0 to this place, it's going to be 2 times 0, that is 0. And substitute x is 0 here, that is sine 0, and sine 0 is still classically 0. So 0 over 0 is still not working. So what we are going to do is to see how to use the L'Hospital's rule again. You can use it multiple times for a particular given question. So let's use the L'Hospital's rule again. So we'll differentiate this side. I will differentiate this side. So this is going to be ln s tends to 0. Division of 2x is 2. Differentiation of sine x, that should be cos x. So now I think it's going to work. So this is going to be 2 over cos 0, and cos 0 is 1. So the answer is R. Repeated option. So the answer is what? 2. So we are going to look at this limit question, see how to do and deal with this. So this is as x tends to 1. Now let's try direct substitution again, which is always the first thing to always what? Try. Now when you substitute 1, you have 0 at the numerator, and definitely you also have 0 at the denominator, so it is an undefined case. So we are going to see how to simplify or use our L'Hospital's rule. Let's use our L'Hospital's rule. Now the differentiation of this term and the differentiation of this term. Now the differentiation of x root x, we can rewrite it as this. Remember, the roots can be s to the power of half, so it's going to be clear as we do the differentiation. Now the differentiation is going to be half x, then half minus 1, which is minus what? Half. Then the differentiation of 1 is 0. So we have the differentiation of x is what? 1. And the differentiation of 1 is what? Is 0. So this is what we actually what? Have after using the L'Hospital's rule. So now we can make a direct substitution. To make a direct substitution, we have half 1 raised to the power of minus half. So this is half, and this is to say 1 over 1 raised to the power of what? Half. This is half times. Of course, 1 raised to the power anything is definitely what? 1. So you have 1. This is half. Now the answer is C. But let's see if we can also look at it from the perspective of trying to simplify this particular expression. Now, to simplify this particular expression, an expression like this, okay, if the roots had been at the denominator, we would have rationalized, but the root is at the numerator. So one thing we can do here is that we can rewrite that denominator. Yeah, we can rewrite that denominator as something like this. We can write it as something like this. Yeah, so that root x times root x is definitely what? X. And minus 1 times 1 is definitely minus 1. So algebraically, this expression is the same thing as this particular expression. So we can cancel out this term. We have this. And now let's see if direct substitution is going to work now. Let's substitute our 1. S tends to 1. So let's see, this 1 is square root of 1 plus 1 is 1 over, of course, square root of 1 is always 1. 1 plus 1 is what? 2. So we still have our what? Half.